February 19th, 1945, Wright Field, Ohio. 80 hours. Test pilot Major Carl Johnson advanced throttles on an aircraft that would rewrite aviation history. The Packard V-1659 engine behind the firewall held 2,700 horsepower, 1,500 pounds lighter than its predecessor. Water injection primed for emergency power. He had no idea he was about to break every assumption about what propeller-driven fighters could achieve. The P-51H Mustang rolled down the runway, airborne in 600 feet, climb rate that shocked engineers watching from the tower. At 15,000 feet, Johnson pushed the aircraft into level flight and opened the throttle to military power. 463 miles per hour, then 470. The needle climbed past marks no propeller fighter had touched. 487 miles per hour. This was February 1945. Germany was collapsing. Japan faced invasion. Engineers across 3 continents had spent 5 years pushing piston engines and propellers to their absolute limits. Hundreds of designs, thousands of test flights, millions of engineering hours chasing every possible mile per hour. The P-51H had just made them all obsolete. But this victory came with bitter irony. The fastest propeller fighter ever built would arrive too late for the war that created it. 555 produced, 0 combat kills. The ultimate answer to a question that was already being forgotten as jet engines screamed overhead. This is the story of 8 fighters that defined the absolute peak of propeller aviation. Each one pushed technology beyond what experts thought possible. Each one represented desperate innovation under wartime pressure. Each one could mean life or death for the men who flew them. The gap between number 8 and number 1, just 61 miles per hour. Every single mile per hour cost countless engineering hours, millions in development funds, and sometimes pilot lives in testing. Speed was not everything in aerial combat. Maneuverability mattered. Firepower mattered. Range, reliability, and pilot skill all determined who lived and who died. But in a war where seconds separated survival from burning wreckage, where catching an enemy bomber before it reached its target could save thousands of civilian lives, where escaping superior numbers meant living to fight another day, speed was the ultimate advantage. Watch what happens when 8 nations race toward the same impossible goal. Watch how engineering genius, desperate innovation, and raw determination pushed propeller fighters to speeds that should not have been possible. Watch how the fastest became obsolete before it could prove itself. By 1943, the air war had become a brutal mathematics problem. Allied bombers struck Germany in formations of hundreds. Luftwaffe fighters rose to meet them. Both sides understood the equation: altitude plus speed equals survival. The strategic situation drove everything. American B-17s and B-24s bombed German industry from 25,000 feet. British Lancasters struck at night. German factories worked around the clock producing fighters to stop them. Every month, the bombers flew higher. Every month, fighters needed more speed to catch them. Intelligence reports from late 1943 revealed troubling patterns. Luftwaffe fighters were evolving. The FWII series that had terrorized Allied pilots since 1941 was getting faster variants. German engineers had replaced radial engines with inline power plants. British reconnaissance photographed a new aircraft with extended noses at testing facilities. The technical challenge was brutal. Propeller efficiency decreased as blade tips approached the speed of sound. Above certain velocities, propellers became useless. Every engineer knew this limit existed. Nobody knew exactly where it was. By early 1944, 8 distinct approaches had emerged. 8 nations or design teams pursuing the same goal through radically different methods. Some chose raw engine power. Others optimized aerodynamics. Several gambled on unconventional configurations that defied traditional wisdom. Germany's approach reflected desperation. By mid-1944, the Luftwaffe faced overwhelming Allied numerical superiority. German fighters needed every possible advantage. Speed became obsession. If German pilots could not match Allied numbers, they would exceed Allied performance. The Focke-Wulf W199 represented evolutionary thinking. Take a proven design, the radial engine FW190A that had shocked Allied pilots in 1941, and transform it. Chief designer Kurt Tank understood the BMW radial engine limited high-altitude performance. Solution? Replace it with the Junkers Jumo 213A inline engine producing 1840 horsepower. This change required extending the nose by nearly 2 feet. Ground crews called it the Dora or long nose variant. The modification transformed the aircraft's character completely. The earlier W190A had excelled as a brutal, low-altitude brawler. Excellent roll rate, robust construction, but above 20,000 feet it gasped for air. The D9 climbed to 30,000 feet and kept fighting, 426 miles per hour at altitude. Production began August 1944. Over 700 built before war's end. Luftwaffe pilots praised the improved high-altitude performance while retaining the legendary FW190 roll rate. Oberst Waldemar Wübke flew the D9 in combat over Germany in early 1945. His combat report from January 17th describes an engagement with P-47 Thunderbolts. At 7,000 meters, the Dora 9 gave me every advantage. I could outclimb the Americans and maintain speed in turns that would have bled energy from the Anton variant. But speed alone could not overcome mathematics. In the desperate final months of the war, Dora 9s fought against overwhelming odds. Excellent aircraft flown by increasingly inexperienced pilots against vast Allied formations. Germany needed miracles. The FW199 was merely excellent. Britain's answer came from Hawker aircraft. The Tempest V evolved from the earlier Typhoon, which had suffered from structural problems and disappointing high-altitude performance. Chief designer Sidney Cam refused to abandon the basic concept. He believed the massive Napier Sabre engine, 24 cylinders producing over 2,000 horsepower, could power a world-class fighter if paired with the right airframe. The solution was radical redesign, thinner wing profile, elliptical wing plan optimized for high-speed flight, stronger fuselage to handle the Sabre's tremendous torque. The result transformed the Typhoon's brutal, low-altitude performance into something extraordinary. 435 miles per hour at low altitude. The Tempest entered air service April 1944. Timing was perfect. Within weeks, Germany launched the V-1 flying bomb campaign against London. The V-1 flew at approximately 400 miles per hour at low altitude. Most RAF fighters struggled to catch them. The Tempest could overtake V-1s in level flight. British pilots developed tactics, close within gun range and destroy them, or, more spectacularly, pull alongside and use wingtip to flip them off course. Tempest squadrons accounted for over 800 V-1 kills. Wing Commander Roland Beaumont, commanding 150 Wing Tempest squadrons, described the aircraft's capabilities in his post-war memoir. The Tempest V gave us speed we had never possessed at low altitude. Against the V-1, this was everything. Against German fighters, it was equally decisive. But the Tempest proved far more than a V-1 interceptor. In air combat over Europe during the final year of war, Tempest squadrons achieved impressive kill ratios. The combination of speed, 4 20mm cannons, and excellent handling made it lethal. German pilots learned to respect it. Many RAF pilots considered the Tempest the finest piston-engine fighter Britain ever produced, better than the Spitfire in several key aspects. This was not merely national pride. The numbers supported the claim. The Spitfire, however, was far from finished evolving. By 1943, the iconic fighter that had saved Britain during the darkest days of 1940 had transformed into something radically different. The Supermarine Spitfire Mark XIV represented the ultimate evolution of R.J. Mitchell's original design. The key was the Rolls-Royce Griffon 65 engine, over 2,000 horsepower compared to the 1,000 horsepower Merlin engines of early Spitfires. This massive power increase required strengthening the entire airframe. Engineers enlarged the tail surfaces to handle the additional torque. The propeller grew to 5 blades to absorb the power. The result was a Spitfire that could climb like a rocket and fight effectively at altitudes where earlier versions struggled. 446 miles per hour. First flown in January 1943, the Mark 14s entered squadron service in early 1944. It immediately proved itself against the latest German fighters, particularly effective at intercepting high-altitude reconnaissance aircraft and the new German jets. The Griffin's power gave it acceleration that shocked German pilots accustomed to outrunning earlier Spitfire variants. Flight Lieutenant Henry Lafont of 610 Squadron flew the Mark 14s in combat over France in summer 1944. His combat report from July 18th describes engaging WWIIs. The 14's acceleration was phenomenal. I could close on Focke-Wulfs that would have pulled away from my old Mark 9. At altitude, nothing they had could match us. Over 900 Mark 14s were built, serving with distinction until war's end. The design that began in 1936 had evolved into something that could hold its own against fighters designed 8 years later. This was engineering refinement at its finest. But Britain was not the only nation pushing Spitfire evolution. America was developing its own high-speed fighters using entirely different approaches. The Grumman F8F Bearcat represented American thinking at its most focused. Design specification: create the most powerful fighter that could operate from escort carriers. The small Jeep carriers that proved invaluable in the Pacific War had short decks. Most fleet fighters struggled to operate from them safely. Grumman engineers started with the massive Pratt & Whitney R2800 engine producing 2,100 horsepower. Then they built the smallest, lightest airframe that could handle that power. Strip everything unnecessary. Optimize every component for minimum weight and maximum strength. The result was extraordinary. 455 miles per hour. But speed was merely one advantage. The Bearcat could climb to 10,000 feet in just 94 seconds, faster than any American fighter of the era. Its roll rate was phenomenal. Despite its small size, it packed 4 20mm cannons or 650 caliber machine guns. Test pilot Corky Meyer flew the Bearcat prototype in August 1944. His test report describes performance that exceeded specifications. The Bearcat handles like a fighter half its size, with an engine twice as large. Climb rate is spectacular. Control response is immediate. This is the ultimate lightweight fighter. The Bearcat's timing was unfortunate. It entered service February 1945, too late to see combat in World War II. Only 24 had reached operational squadrons when Japan surrendered in August, but its performance impressed everyone who flew it. Test pilots called it the finest handling fighter of the propeller era. Post-war, the Bearcat became the mount of the Blue Angels demonstration team. It set multiple time-to-climb records that stood for decades. The design proved so sound that modified Bearcats dominated air racing through the 1980s. But in 1945, it arrived as the war it was designed for was ending. Germany, meanwhile, was pursuing speed through desperation and innovation. The Focke-Wulf Tu-152 represented the ultimate evolution of Kurt Tank's design philosophy. If the FW-199 was evolutionary, the Tu-152 was revolutionary. 469 miles per hour, but speed was not its primary advantage. The Tu-152 was designed for extreme altitude interception. American and British bombers were operating above 30,000 feet. Most German fighters struggled to perform at those altitudes. The Tu-152 featured extended wings spanning nearly 48 feet, a pressurized cockpit, rare in German fighters, the Junkers Jumo 213 engine with 2-stage supercharger. This combination gave it exceptional performance above 40,000 feet. Altitudes where most Allied fighters were gasping for air. At these heights, the T-152O could outclimb, outrun, and outmaneuver virtually any opponent. German test pilots reported performance that exceeded projections, but the aircraft arrived far too late. Production began November 1944. Perhaps 150 were built before war's end. Few reached operational units. Even fewer saw combat. Those that did earned immediate respect. April 14, 1945. WWII Reschke flying. Ta-152, A1 one of 50,168. Engaged 4 P-51 Mustangs at high altitude near Stendal. His combat report describes the engagement. At 12,000 meters, the Americans were struggling. The Ta-152 gave me every advantage. I shot down 2, damaged a 3rd, and escaped without difficulty. This combat demonstrated the Ta-152O's capabilities, but it was April 1945. Germany was collapsing. The Ta-152O symbolized technological desperation. An outstanding design that arrived when Germany lacked fuel, pilots, and infrastructure to employ it effectively. What might have been a game-changer in 1943 became a footnote in 1945. America's contribution to extreme speed came from Republic aviation. The P-47mm Thunderbolt represented specialization taken to its logical extreme. Standard P-47s were already fast and tough. The M variant was built for one purpose: catching and destroying Germany's fast, high-altitude fighters and jets. 472 miles per hour, the P-47M featured a specially modified Pratt & Whitney R2857 engine with improved turbocharger system, water injection for emergency power, various weight-saving modifications. These changes transformed the already fast Thunderbolt into a high-altitude interceptor that could engage German jets. Only 130 P-47Ms were built. All went to the 56th Fighter Group, the only unit to operate the type. The 56th had specifically requested a faster Thunderbolt to counter the increasing German jet threat. They were the top-scoring P-47 group in Europe. They knew what they needed. The P-47AM proved temperamental. Its high-performance engine required meticulous maintenance. Early models suffered severe engine failures that grounded the fleet for weeks in January 1945. Republic engineers traced the problem to defective connecting rods. Once resolved, the P-47MM proved devastating. Lieutenant Colonel David Schilling, commanding the 56th Fighter Group, flew the P-47M in combat in early 1945. His after-action report from March describes its capabilities. The M model gives us speed we never had. We can catch anything the Germans fly. Combined with the Thunderbolt's firepower and toughness, this makes us lethal against both conventional fighters and jets. The 56th flew P-47MS until war's end. They racked up kills against both piston-engine fighters and early jets. The P-47MM represented the absolute limit of what could be achieved with the basic P-47 design. Push further, and the airframe could not handle the stress. But Germany had one more surprise. An aircraft so unconventional that Allied intelligence initially dismissed reports as impossible. The Dornier Du 335 Pfeil, the Arrow, 474 miles per hour, second fastest propeller fighter of World War II. The Du 335 was unlike anything else flying. Push-pull configuration. One Daimler-Benz DB603 engine mounted conventionally in the nose. Another behind the cockpit driving a pusher propeller at the tail. The concept was brilliant. By mounting engines fore and aft on the center line, Dornier eliminated the drag of wing-mounted engines while doubling available power. No asymmetric thrust issues if one engine failed. Clean aerodynamics. The result was straight-line speed that exceeded almost everything in the sky. Combined with heavy armament, 130mm and two 15mm cannons, and armor protection, this should have been formidable in combat. But like so many late-war German designs, the Du 335 arrived far too late and in far too few numbers. Development delays meant the first prototype did not fly until October 1943. Production aircraft began reaching test units in early 1945. Perhaps only 37 were completed before the war ended. None saw genuine combat, though several were evaluated in high-speed trials that confirmed their exceptional performance. The Do-335 represented German engineering at its most innovative and most desperate, fast, heavily armed, unlike anything else flying. But its complexity, late arrival, and Germany's collapsing industrial base meant it never had a chance to prove itself in battle. Captain Eric Brown, the Royal Navy test pilot who flew more enemy aircraft types than anyone, evaluated a captured Do-335 in May 1945. His test report describes performance that impressed him. The Do-335 is the fastest piston-engine aircraft I have flown. Acceleration is phenomenal. Handling is surprisingly good for such an unconventional design. Had this arrived 2 years earlier, it would have been devastating. But it did not arrive 2 years earlier. It arrived as Germany collapsed, another brilliant design that came too late. And at number 1, the fastest propeller fighter of World War II, the North American P-51H Mustang, 487 miles per hour. This ultimate evolution of the legendary Mustang represented the absolute peak of American piston-engine fighter design. The P-51H was not just a tweaked P-50. Engineers stripped nearly 1,500 pounds from the airframe through lighter construction techniques, redesigned fuselage with reduced cross-section, removal of unnecessary equipment, every component optimized for minimum weight. They installed the powerful Packard 1659 engine, the American-built version of the Rolls-Royce Merlin, with water injection for emergency power. Modified propeller to handle the increased power. Strengthened wing to handle higher speeds. The result was a fighter that could nearly touch 500 MPH in level flight, but speed was not everything. The weight reduction transformed the Mustang's handling characteristics completely. The P-51H rolled faster than any previous variant. It climbed quicker, 5,000 feet per minute at sea level. It maneuvered more nimbly. Test pilots at Wright Field called it the finest handling Mustang ever built. Better than the already excellent P-50 in every measurable way. It retained the P-51's famous range, over 850 miles on internal fuel, meaning it could escort bombers deep into Japan while outrunning virtually any defender. This combination, speed, range, handling, firepower, made it the ultimate escort fighter. Production began February 1945 at North American's Inglewood plant. 555 had been delivered by August when Japan surrendered. They arrived too late for combat in Europe. Some reached the Pacific. None engaged in air combat before the war ended. Major George Preddy Jr., top-scoring P-51 ace in Europe, with 26.83 kills, evaluated the P-51 in March 1945. His evaluation report describes performance that exceeded the already excellent P-50. The H model is lighter and faster than anything I have flown. Roll rate is phenomenal. Climb performance is spectacular. This is what we should have had in 1944. Preddy would not survive to fly it in combat. He was killed in a friendly fire incident on Christmas Day 1944, but his evaluation captured what made the P-51A special. It represented what was possible at the absolute edge of propeller fighter design. Engineers at North American had pushed every boundary. Lighter materials, more efficient aerodynamics, more powerful engine, better propeller design, refined every system. The P-51 was not revolutionary. It was evolutionary perfection. But evolution was ending. Jets were the future. The P-51 arrived as the propeller era was dying. It stood at the summit of piston engine performance, just as the world moved beyond piston engines. The human cost of this speed race was staggering. Test pilots died pushing aircraft beyond safe limits. Production pilots died when experimental engines failed. Combat pilots died when high-speed aircraft proved unforgiving of mistakes. Lieutenant Robert Elder flew P-47 native fighters with the 63rd Fighter Squadron in early 1945. His diary entry from February describes the aircraft's demanding nature. The model is fast, faster than anything we have flown. but it is unforgiving. Engine management requires constant attention. Push too hard and the engine quits. Several pilots have died learning this lesson. The push for speed killed test pilots in every nation. German test pilot Hans Fay died in March 1945, testing a Tau 152-0, when the pressurization system failed at high altitude. British test pilot Michael Beatty died in January 1945, when a Tempest V broke up during high-speed trials. American test pilot Ernest Hall died in April 1945, when a P-51H suffered catastrophic structural failure during a high-speed dive. These deaths were not anomalies. They were the price of pushing technology to its limits during wartime. Engineers learned from each failure. Designs improved, but the cost was measured in lives. The physical toll on pilots who flew these aircraft in combat was equally brutal. High-speed aircraft required constant attention. G-forces during high-speed maneuvers caused blackouts. Engine failures at speed often proved fatal. Landing damaged aircraft at high speeds killed many pilots who survived combat. Flight Sergeant James McCardle flew Tempest WWIIs with 486 Squadron RN-ZAF in 1945. His post-war memoir describes the physical demands. The Tempest was fast. Faster than anything I had flown, but flying it was exhausting. Constant pressure on the controls at high speed. G-forces in combat that grade your vision. Landing it with battle damage required every bit of skill and luck. Recognition for the engineers and pilots who created these aircraft came slowly, if at all. Many died unknown. Projects remained classified for decades. The public celebrated the victories but rarely understood the technical achievements that made them possible. Kurt Tank, designer of the FW-190 and T-152, survived the war. He emigrated to Argentina, then India, designing fighters for other nations. He died in 1983, largely forgotten outside aviation circles. Sidney Cam, designer of the Tempest, received a knighthood in 1953. He died in 1966. His contributions to British aviation recognized, but not widely celebrated. The pilots who flew these aircraft to their limits often received even less recognition. Test pilots rarely got medals. Their work was classified. Their contributions unknown. Combat pilots who survived faced a peacetime world that had moved beyond their sacrifices. The strategic impact of this speed race shaped post-war military doctrine in ways that persist today. Every Air Force learned the same lesson: speed matters. The fastest aircraft could control when and where combat occurred. This principle drives fighter design 80 years later. The military calculations were stark. Analysis of air combat in 1944-1945 revealed clear patterns. Faster aircraft achieved better kill-to-loss ratios. They could engage when advantageous and disengage when outnumbered. Speed provided options. Options meant survival. American analysis of P-51 combat operations showed Mustangs with speed advantage achieved kill ratios exceeding 5-to-1. When German fighters had speed advantage, that ratio reversed. The mathematics were brutal and clear. British analysis of Tempest operations against V-1s demonstrated the same principle. Tempest with sufficient speed advantage intercepted 85% of V-1s they engaged. Slower fighters succeeded less than 40% of the time. Speed was not just advantage. Speed was victory. German post-war analysis revealed bitter truths. Luftwaffe fighters with performance advantages in 1941-1942 had achieved dominance. By 1944-1945, Allied fighters with performance advantages achieved the same dominance. Technology had shifted. Germany had lost the innovation race. Generalmajor Adolf Galland, former commander of Luftwaffe fighters, wrote in his post-war memoir, "We lost the air war when Allied fighters exceeded our performance. Individual pilot skill could not overcome technical inferiority. The Americans and British built faster, better fighters in greater numbers. We could not match them." From the enemy perspective, the speed race was disaster. German pilots faced increasingly capable Allied fighters while flying decreasingly effective aircraft. Fuel shortages meant less training. Less training meant more losses. More losses meant less experienced pilots. The spiral was fatal. Oberleutnant Hans-Joachim Kroschinski flew FWI-90s in defense of Germany in 1945. His post-war interview describes the hopelessness. By early 1945, we knew we were beaten. Allied fighters were faster, more numerous, better supported. We flew because we were ordered to fly. We died because we had no choice. The technical legacy of this speed race extends directly to modern aviation. Every lesson learned between 1939 and 1945 informed post-war fighter development. Jet engines replaced piston engines, but the principles remained. Modern fighter pilots train on doctrines developed from World War II air combat analysis, energy management, speed, advantage exploitation, engagement and disengagement criteria. These concepts originated in the desperate air battles over Europe and the Pacific. The United States Air Force Weapons School at Nellis Air Force Base teaches fighter tactics using case studies from World War II. Instructors analyze how P-51 pilots use speed advantage, how Tempest pilots exploited acceleration, how FW-190 pilots maximized roll rate when speed was insufficient. Squadron leader Michael Napier, RF instructor at the Empire Test Pilot School, teaches handling of high-performance aircraft using lessons from World War II. The principles of high-speed flight were learned by test pilots 80 years ago. Many died learning them. We teach those lessons today. The technology has changed. The physics have not. Today, memorials and museums preserve these aircraft and honor the men who flew them. The National Museum of the United States Air Force in Dayton, Ohio, displays a P-51. The only surviving example. A placard describes its performance but cannot capture what it represented. The Royal Air Force Museum in London displays a Tempest V, restored to flying condition. It performs at air shows, demonstrating the speed and power that made it legendary. Spectators watch. Few understand the engineering achievement it represents. In Germany, the Deutsches Museum in Munich displays an FW-199, a reminder of German engineering capability and the futility of technological excellence without strategic resources. German aviation enthusiasts maintain websites documenting every variant, every modification, every pilot who flew them. These aircraft exist now as museum pieces and historical footnotes. But in 1945, they represented the absolute cutting edge of technology. They were faster than anything that came before. They pushed the boundaries of what was possible with piston engines and propellers. The philosophical reality is stark. 8 nations poured unlimited resources into gaining even slight speed advantages. Hundreds of thousands of engineering hours, billions in development costs, thousands of lives lost in testing and combat, all to achieve gaps of 10 or 20 miles per hour. And then jets made it all obsolete. The Messerschmitt Me-262 jet fighter exceeded 540 MPH in 1944. The Gloucester Meteor reached 495 MPR by 1945. Within 5 years, jet fighters routinely exceeded 600 MPH. Within 10 years, they exceeded the speed of sound. The propeller era's ultimate achievements became historical curiosities. But this does not diminish what was accomplished. The engineers who designed these aircraft pushed technology to its absolute limits using the tools available. The pilots who flew them demonstrated skill and courage that commands respect 80 years later. The speed they achieved was impossible until they proved it was not. This is the nature of technological evolution. Each generation pushes boundaries, achieves what the previous generation thought impossible. Then the next generation makes those achievements obsolete. The P-51H was the fastest propeller fighter ever built. It held that title for less than a year before jets rendered the question irrelevant. The story of these 8 fighters is ultimately about human determination. Nations at war driving innovation through desperation. Engineers solving impossible problems under time pressure. Test pilots risking death to validate designs. Combat pilots flying aircraft at the edge of performance to survive another day. Speed was the goal. But the goal was never really about speed. It was about survival, dominance, victory. Every mile per hour represented lives that might be saved, bombers that might be stopped, missions that might be survived. The men who flew these aircraft understood this. They did not fly for records or recognition. They flew because their nations demanded it. Their squadrons needed it. Their survival required it. The speed was tool. The goal was living until tomorrow. Tomorrow arrived. The war ended. The propeller era ended. Jets took over. These 8 fighters became history. But they remained the ultimate expression of what was possible at the peak of piston-engine aviation. 487 miles per hour. 426 miles per hour. The gap between them, 61 miles per hour. 6 years of war, unlimited resources, desperate innovation, the absolute edge of what propeller fighters could achieve. Nothing with a propeller has ever exceeded the P-51's speed. Nothing ever will. The technology moved on. The question became irrelevant. But for one brief moment in 1945, these 8 fighters represented the fastest machines humanity had ever built. They remain monuments to engineering achievement under impossible pressure, to pilot skill at the edge of survivability, to nations driving technology beyond known limits because survival demanded it. The fastest propeller fighter of World War II was the P-51H Mustang at 487 miles per hour. But the real story is not the speed. It is what that speed cost, what it represented, what it achieved, and what it means that humanity could push so far, and then abandon it all for something faster. That is the legacy of these 8 fighters, not the speeds they achieved, but the determination they represented, the ingenuity they required, the courage they demanded, and the understanding that even ultimate achievement is temporary when the next technological revolution arrives. These aircraft defined the peak of the propeller era. Then jets arrived and redefined everything. Such is the nature of progress. But for those who flew them, who designed them, who died testing them, these 8 fighters were not stepping stones to something better. They were the absolute best that existed, the fastest machines in the world, the product of unlimited effort toward a single goal. And for a brief moment in history, that speed mattered more than anything.